As you can see from the previous video section, the proof of the prime number theorem involves a comprehensive understanding of this function v as well as its average we just defined. So to finish our elementary proof of the prime number theorem, we need two lemmas to bound the integrals involving v. The first lemma states that if you integrate the function v over any interval, you get a uniform bound. Specifically, there exists a fixed positive number a1, such that for every positive number c1 and c2, we have this integral is uniformly bounded by this constant a1, independent of the choice of c1 and c2. Note that here, the absolute value is on the integral, not on the function. We can also put this theorem in another way. Just say the supremum for all c1 and c2 bigger than 0 of the integral absolute value is finite. This is our first lemma. Now let's prove this. We first write the integral from c1 to c2 b eta d eta as a difference, the integral from 0 to c2 and the integral from 0 to c1. Now, by the triangular inequality, to show that this guy is bounded by an absolute constant, it suffices to show these two are bounded by absolute constant, respectively. And now, we use the definition for v and perform a change of variable here. We let t equal to e to the eta, and therefore eta is equal to log of t. If we plug this back to the integral, what do we get? Eta moves from 0 to c, so t moves from 1 to e to the c. Now, why is this guy uniformly bounded? Let me write one more step, and then you'll see. We'll do a truncation at 2. And if you still don't see at this point, let me do one more step. From here, first, observe that the first integral is from 1 to 2, and the integrand is bounded. The third integral can be computed. This is equal to log of e to the psi minus log of 2. What is really interesting is this middle term. This guy is something that we have seen before. Specifically, this is the equation 22.6.1. And previously, we have shown that this integral is log of e to the c plus big O of 1. Therefore, log of e to the c cancels with log of e to the c. And we are only left with absolute constants. This is an absolute constant, this is an absolute constant, and this is an absolute constant. And we are done with the proof of this lemma. And here, the reason that we chose this 2 truncation is just that we want to use 22.6.1 more precisely. And strictly speaking, you don't really have to pick this truncation. If it is from 1 to e to the c, this 22.6.1 should also work. The second lemma we want to establish is the following. First, recall the definition for alpha. Now, if it naught is positive and is the root of the function v, then we have the integral from 0 to alpha of the function v of it naught plus tau d tau, and here's the absolute value inside. And by translation, this integral is equal to the integral from it naught to it naught plus alpha of v of tau d tau, absolute value inside. This part is just by changing variable. The conclusion of this lemma says this integral is bounded by 1/2 times alpha squared plus big O of it naught inverse. In the proof, you will see that you may replace this alpha by something else. But then you have to change this big O of it naught inverse to something else. Later, we're just gonna use this lemma for the integral from 0 to alpha, and that is why we state it in this way. The proof of this lemma is more involved than it looks. Actually, it involves the Selberg's asymptotic formula. Specifically, we're going to use 22.14.2, which says as follows. Now, we're going to rewrite this formula by replacing this part by something else. By the definition of psi, we know the sum is equal to, and if you combine this into one sum, this is what we get. And you have seen this argument before, when we prove that this formula is equivalent to the other one in Selberg's theorem. So now we're going to use this formula. Now, for x naught bigger or equal to 1 less than x, we substitute this x by x naught, and we subtract both sides of this equation by both sides of this equation, with x naught replacing x. Because x naught is less than x, we can merge these two big O's together as big O of x. And now, observe that psi of x and log of x are both monotonically increasing, and they are non-negative. And this part is always non-negative. So we have the following relation. Since psi, log are both monotonically increasing, and lambda is non-negative, we obtain this inequality. Now let's continue from here to see what this guy can give us. We consider the following difference. We look at r of x, log of x, minus r of x naught, log of x naught. By definition of r, what is this? This is equal to psi of x minus x times log of x minus psi of x naught minus x naught times log of x naught. And if you break the parentheses, we can use this result above, which says this part is bounded by this thing. So if you plug this into here, we get the upper bound, which simplifies it to, on the other hand, if we simply look at that psi of x times log of x minus psi of x naught times x naught be equal to 0. From here, and if we replace psi of x by r of x plus x, and similarly for psi of x naught, we'll get, and if we move the terms here that don't involve r to the left hand side, what do we get? We will get a lower bound for this difference. And now combine this upper bound with this lower bound. We have the absolute value of the difference r of x log of x minus r of x naught log of x naught. This absolute value less than or equal to the difference x log of x minus x naught log of x naught. This guy is always positive because of our assumption, plus big O of x, resulting from here. Remember, our goal is to establish an upper bound for the integral involving v. But so far in the proof, the letter v has not appeared yet. But that is what we're gonna do next. We'll do substitutions on the variable x and x naught, and then you will see v appearing. So now put x naught equal to e to the eta naught, where eta is positive and is the root of v, as in the hypothesis of this theorem. And it follows that r of x naught is equal to r of e to the eta naught which is the definition of v e to the 8 naught times v of 8 naught, which is 0. And put x equal to e to the 8 naught plus tau, with tau bigger or equal to 0. Then r of x is equal to r of e to the 8 naught plus tau, and we pull out this exponential, and the remaining part will be v of 8 naught plus tau. This is simply the definition for v. And at the same time, log of x is equal to 8 naught plus tau. Now, the left-hand side will become what? The left-hand side of this inequality will become, because now r of x naught is equal to 0, so there's only one term for this absolute value. That is 8 naught plus tau times e to the 8 naught plus tau times the absolute value of v of 8 naught plus tau. And the right-hand side of this becomes e to the 8 naught plus tau times 8 naught plus tau minus e to the 8 naught times 8 naught plus big O of e to the 8 naught plus tau, simply by substitution. So this inequality will become, if we divide both sides by this part, 8 naught plus tau times e to the 8 naught plus tau, we will get an upper bound for the function, the absolute value of v of 8 naught plus tau. This is bounded by 1 minus e to the negative tau 8 naught divided by 8 naught plus tau plus big O of 1 over 8 naught plus tau. And now let's rewrite this by separating the variable tau and eta. Now let's focus on these two terms. First, it's easy to see that this part is a big O of 1 over 8 naught. This is simply because this 1 over 8 naught plus tau is bounded by 1 over 8 naught, since tau is non-negative. Now what about this part? I claim this part is also a big O of 1 over 8 naught. And let's simply check this by definition. To check this, we'll divide this term by 1 over 8 naught, which means we multiply this guy by 8 naught. This is a positive thing, and it is upper bounded by, we can throw away this denominator and become tau times 8 naught divided by 8 naught, which is tau. So this is upper bounded by e to the negative tau times tau. But this thing is always bounded by 1, which verifies this claim. Therefore, we have as value of v of 8 naught plus tau is bounded by 1 minus e to the negative tau plus big O of 1 over a naught. By calculus, we know this term is always less than or equal to tau. So now we get a really simple upper bound estimate for v of a naught plus tau, given that a naught is a positive root of v. Now we can finish the proof of this lemma. Using this upper bound, using antiderivative, this is alpha squared divided by 2 plus, for the other term, it is big O of alpha divided by a naught. But alpha is an absolute constant. So we can remove the alpha from here. This is simply alpha squared divided by 2 plus big O of 1 over a naught. And that finishes the proof of this lemma. And for the proof, you can also see if alpha is not this specific number, then this integral will be alpha squared divided by 2 plus big O of alpha divided by a naught. But later, we're just going to use this with this particular alpha, as stated in Harday's book.